Yo, welcome back everybody, ni hao! Today, you are either watching this live as a recording on YouTube you're either watching as a recording on YouTube or my live broadcast on Red Note. Right, does that work? Yes. Okay, alright, cool. Sweet. So, this is a problem from yesterday, and the question that I just asked, and now I'm starting to look at, is how do you find the inverse of A? And that's what we had to do, right? So, a little bit of editing magic. Shada! Here's my scratch work for finding the determinant. Now, I worked through the problem exactly like I assume you guys did. There's one little thing that I would change about the way that I've done it. But what I want to do is you guys can try to jot really, really fast. But I think there's more value in if you pay attention rather than just trying to write down character by character, right? Like, this is on the video. If you want it in your notes, you can include it in your notes. Today, we're going to use this idea to find a faster, more efficient way to go through stuff. So, with that said, if you are jotting this down and just copying, I would say pause it now. If you want it in your notes, come back and get it. Let's just talk about it so we can make sure that everybody's on paying attention to this rather than the writing part. Okay, here's what you guys just told me to do. You said find the determinant. 1 times 1 minus 12. 1 minus 12 is negative 11. Okay, negative 1/11th. I only move it because I think it's annoying when there's a negative in the denominator. Here's 1 over the determinant, and then here is that adjoint, right? Where we swap the stuff around. Okay, here's my inverse. Now, once I have the inverse, and it's written in green here, that's all my scratch work, and really there's a lot of scratch work with linear algebra stuff and matrices. But here's where I roll. This is where we left yesterday. I said, let's multiply by the inverse on the left and the right. So I did the same thing. Here is, I didn't show the work, but here is what I got when I multiplied A inverse times A. And this is me expanding it out because unless they're physically written next to one another, I can't do it in my head. I had to do this one. I just looked at A here and the inverse here, and this is how I did this multiplication. Now, I know that it should come out to be the identity matrix. That's what it means to have an inverse. However, if I don't take the time to actually do A inverse times A, and verify that I'm correct, the rest of my problem, if my inverse is wrong, the rest of it's nonsense. This is just me checking. Now, you could conceivably not have any of this yellow part showing if you're super confident in your inverse, but the risk of being wrong and never knowing it is exponentially greater here. Okay, so this is A inverse times A, and then I expanded it and it was the identity. So I'm convinced that this was the inverse. Is everybody cool with just this left side right now? I'm talking really fast. I multiplied using that row by column idea, and these are the numbers that spit out, and it turns into the identity matrix. Okay, so from here, I do the work, and then this is really A times A inverse is the identity, which I know is still times xy, because that's what my equation said. And then eventually we'll multiply this by xy, and we'll just get xy. I've only looked at the left side right now. Okay. On the right side of this equation, we still have to do the algebra both sides equal. I multiply both sides by A inverse. So here it is, and here's what was on the right side of the equation. Now, this one's weird because you only have, good on you, that's a good friend move. You only have a 2 by 1, so the multiplication feels weird, but it's way faster. When I multiply on the right side of this equation, A inverse times this negative 13/8, here it is. I do the work, and this is what I come up with, and I'm just doing it because I can't do matrix stuff in my head well, and I wind up with this after I do it. Now, this comment in white, I don't mind fractions. They're okay, but I agree with, I imagine all of you, that no fractions or less fractions is easier. What we could do, and what I would do if I was doing this problem on my own, is instead of actually distributing this through, I could have just kept it out front and done the multiplication and then distributed at the end. Because I know that I can scale it first or later. It doesn't matter. That's how I would normally do it. That's okay if you're hearing that and thinking, what? That's fine. When I multiply it, I get these and I add them up, and here's the numbers that I get. And I think it's negative 1 and 4. Okay. When we get to this point, notice, top is x equal to top here is negative 1. Bottom is y is equal to 44/11 or 4. Because we've solved the system, what should I always do with these values of x and y? Before I actually write my answer, because my answer is not quite showing. plug it in, check to make sure it works. Okay, now looking at it. Here is my original system, and we're claiming -1 and 4. That's what I came up with. If I do -1 minus a -12, is it -1 minus 12, I'm sorry, is it -13? If I do 4 plus 4, do I get 8? Okay, I have found the solution to my system. I'm convinced of it, and here it is. Now, I feel like I just keep saying it and then unsaying it and saying it and unsaying it. This is just a different way to solve a system, right? Is this easier or harder than elimination or substitution? It's harder. Now, whether or not I agree with you on the actual computational difficulty, I don't know. I think this is a lot more work to solve the system. Do you guys agree? Like, just substitution or elimination is easier than this. Easier, quote unquote. Okay, now, because I think that's the case, and I assume you guys think the case, I don't know that there's a ton of value in us solving every single system like this. This doesn't save us any time, right? It's a different way to think about it. It's how a computer would do it. But in our purpose, there's no increase in efficiency yet. If I give you a 3x3 system of equations, so x, y, z with 3 equations, you guys solved those last year in Algebra 2. It's a long process. You have to solve one in terms of the other 2 variables. You do substitution, now you get a bigger complex system. And we're not going to go over how you do it with the algebra. It's just big substitution is what it winds up being. Okay, 3x3s suck to do the algebraic way. They do. 2x2s aren't bad. Now, here's what I'm thinking. This method works, and it works for really big matrices because we can do all the same stuff. However, in my opinion, if we had a nice way to streamline this process, like to make it just say, let's just plug and chug, which is my least favorite kind of math, but factoring is hard, right? Typically, kind of, depending, can be. There's a lot of thought that goes into factoring. Is there a lot of thought that goes into the quadratic formula? Like, I mean, if I have it, I just put in the numbers and I just plug them in and it spits out the answer, right? Now, that is valuable once you know how to factor. It's a huge time saver. I don't like the idea of using quadratic formula to factor all the time, so I stress not to do that. Similarly, though, I don't think that this is the most efficient way to do it. So today in class, and it's just going to continue on with your notes, we are first going to turn off the biology notes because that's where I wrote the solution there. Just a reminder, if you are dying to have all of this equation in your work today, or in your notes, where could you find it? Because I'm not going to sit here and wait 10 minutes. Yeah, YouTube, check the Red Note broadcast later. I'm going to make that joke like forever, just so you guys know. No, not a chance. Okay. Yep, no. Cool. All right, so I'm just going to get that out of here. Today, here is my discovery kind of thought. We're going to learn about something called Cramers' rule. And Cramers' rule, as you can see here, this is the plug and chug version of solving a system. You don't have to really think about it. You just have to do the operations. Now, historically, when I've taught Cramers' rule, and I imagine you guys probably saw Cramers' rule last year in Algebra 2, but I don't know for sure if it was the online stuff. I can't tell. However, I want you guys, let's derive this. And by let's, I mean I want you guys to get us started deriving this. And we're going to see if we can't figure out Cramers' rule. I have some guided steps along the way. For now, we're going to see if we can't derive it, which just means see what is the formula, let's find it for ourselves, rather than me just saying, here it is, use it. This is much more valuable. Now, as far as what I want you to actually write down, this section is what you should have written in your notes. Up to that first asterisk. Don't include the first asterisk. All I need you to have is Cramers' rule, what it is, it's a plug and chug method, and then we're going to derive it using this 2x2 system. Now, when we look at this, this is where I'm not quite sure how to do this the right way. I want you guys, we're going to check in at each one of these. Each one of these asterisks is like a part A, B, C, and D. but I don't care. I'm not going to make you derive this again, but we are going to do it today in class. First thing that I want you guys to do, and I'm going to pause it, once you're done, we'll check. If you get the right setup here on this first asterisk, I'm going to ask that you check with your neighbors, check with whomever, make sure that we can all get this done. Once we all have this first asterisk, we'll move on. And we're going to move together as a unit, but we get this idea of we're seeing where this really happens, and we're going to work it out. Okay. So, for a moment, and the video is going to be wonky for those of you watching, you're just going to have to pause it. Right now, I want you, if you're watching the video, pause it. Everybody in here, and I don't know if they paused it when I said that or not, because if they did, this isn't going to make sense anymore, so we'll see. Everybody in here, if you have this written, the given ax plus by equals c and dx plus fy equals g, I want us to write this as a matrix equation. If that was an F-bomb, hold those out or back. Okay. Do you understand what I'm saying when I say write this as a matrix? Yep. Okay, if you don't, look at the very last thing that we did yesterday, or just as a reminder of it, here was a system of equations that we had yesterday. Right up here, here's our system, right? This was this matrix equation that we had. Cool. You need a coefficient matrix, a variable matrix, and a constant matrix is what we referred to it yesterday. I don't care if you write this yellow part down, it's entirely up to you. But step one, take this system and write it as a matrix equation. You will see the solution in 3, pause it now, you'll see it after the resume. In 3, 2, okay, step one. We have converted this system into a matrix equation. Now, it's essentially the same problem that you guys did or didn't, depending, but on the assignment last night. From this, it's weird because there's no numbers. Could we find A inverse? Now, there's a couple ways that we can write this, and this one I want to do kind of together because it feels strange, but that 1/11th comment that I made when we worked through the problem that it's easier just to do it later, I'm not going to distribute that through yet. I'm just going to keep it as a constant or a scalar out front. So I'm going to move everything down first and foremost so I have room to write, but we have it. And notice here's A, it's our coefficient matrix. This is X. Yesterday I think we called it B, I think. And this is B in this situation. What we name it doesn't really matter, just so you know. Okay, now moving all this stuff down, how do we find the inverse? A inverse. What's the scalar out front? 1 over. So I heard both of them. Somebody said FA minus BD. You're not wrong, but I also think that I'm not wrong. Do you guys agree with that? Okay. I'm not going to distribute this through yet, but I'm going to multiply this by that adjoint matrix. That is the name of it, but since the wonky change, right? And what's that wonky change? So a bunch of stuff flips and changes, right? So if I take the adjoint of A, what would it become? F, negative B, negative D, delta, and A alpha. Now, without expanding, anybody have issue, questions, concerns, misunderstandings as to what I've done? Okay, it's strange with no numbers, but this is exactly what we do. Okay, now, if we were trying to solve this equation and I wanted only xy left over here, we have to, and I think you can see the answer, but what do we have to multiply to undo matrix A? A inverse. Now there's no numbers in here. There's no concern on my end, hopefully your end, that we've written something down wrong. There's no numbers to worry about. So I can't even check it to multiply. I know that once I do this onto both sides, and I'm going to write it here in green, but I don't want you to write it. I'm doing A inverse times this and A inverse times this, right? On the left specifically. Left of each expression. What's going to remain on the left side of this equal sign? A inverse times A times X. What would remain if you had A inverse times A times X? It's X, right? And I don't like that I can't move that, so I'm just going to do Hey, it's letting me change it. Cool. All right, so we would just have matrix X. Everybody cool there? Now, I'm trying to skip, not truly, but get by a little bit of work. If I do this to both sides, I think what I get is X over Y, this is matrix X, that remains on the left side of the equation. Everybody on board with that? Only thing I didn't show is the identity times that, which is still just this. On the right side, and this is ugly, but I think if we just plug and chug right through, instead of writing A inverse, we just found that this is A inverse. F, negative B, negative D, A. Okay, this is the inverse, right? And this is where it looks ugly because we didn't distribute. That by itself is A inverse. What were we still multiplying by on the right side? So we had A inverse times A times X on the left equals A inverse times B. And what was matrix B? C and G, golf. Okay. All right. Now, I really want to stress the importance. If there's anything up here that doesn't click yet, before we move forward, we should cover it. Issues, concerns, questions, things that you don't quite get, any part about this. Operationally, everybody's okay with what's happening. Okay, so now, here's what I want you to do for me. It's going to be ugly for just a second, and I'm trying to make it so you don't see this big rule that is about to be revealed to us. I want you guys to do this last part. I want you to actually multiply this right side, and I know it's going to be ugly for a second. Do the multiplication, just using regular stuff, and on the left, you're going to have X and Y. Cool. And I'm asking specifically about X, but I could have asked for Y, and if you do all of it, you're going to do both. I want you to expand out this right side, multiplying those things together. There's no numbers. I would not distribute this through. I would multiply these two. You can multiply the 1 over the determinant through if you want, but do this matrix multiplication right here and see if you can tell me in general what X is equal to, or Y is equal to, or both in general. I'm going to give you a minute. I want you guys to do this multiplication and see if you can't come up with a rule. Okay, so if you're watching this on the road, you will pause now, do this multiplication, show me you understand the multiplication, and you'll see why this FC minus BG question spits out momentarily. Cool. All right, pause it now, try to do this multiplication and address that question, and I'll see you guys in 3, 2, 1. Okay, looking at it, the mistake that I've missed. Seems like all of you followed my advice. I'm going to leave an awkward spot here because this is a number times a matrix times a matrix. I'm going to do the matrix times matrix part first. So what I saw a lot of people forget is what's the number that we're not going to just lose? 1 over the determinant. Now, if you've already written it, don't erase. If I take 2 times a matrix, and you don't have to write this, just me talking, 2 times 1, 1, 1, 1, it's 2, 2, 2, 2. Is that the same thing as if I do 1, 1, 1, 1 times 2? Okay, so if you didn't include this 1 over the determinant, you can write it on the right side of it. Like, it's okay. Now, I have 1 over the determinant of A times, and when we do this, we get F, so row to column, F times C minus, or plus rather, but it's plus and negative, BG. Are you guys cool with that? Okay, in the denominator we get what? Negative DC plus AG. Okay, we now have this. Now, that last part, it's a lot of writing if I want to be really precise with the way that I'm questioning. If you got to this point, I'm feeling real good with this. Because I now have a way to say what X is, but I need one more little step to see how we can replicate this process without having to do the same thing over and over and over. When I see this, it looks like FC minus BG. Now, there's an operation that we've seen where you take this times this minus this times this. What is that operation? It's the determinant. Now, We could do this for X or for Y, just so you know. I'm only looking at the X's right now, okay? So I'm only looking at the top. If I think of FC minus BG, it's the determinant of something. And more specifically, I want you guys to include this. FC minus BG is the determinant, and I'm just going to say is determinant, of, what would that matrix be? F and B and G and C. Do you guys agree with that? Okay, bigger question, and you can't see it on my screen, but you can see it in your notes. How does this matrix relate to our original system of equations? And more generally speaking, if we had actual numbers, how would you know what goes in where into this? That sounds really vague, and the eyebrow directions made me think that that might have been a little bit too vague.
Why is it FBGC?
Sorry?
Why is it FBGC now? Where's it at?
What are you talking about, the determinant of A?
You said in the bottom line.
FC minus BG, so that's the top part, right? We're only doing the X's. I could have, if I wanted to do all of it, I could have said similarly, where does this come from? Negative DC plus AG is the determinant of what? I'm only doing half of it, because the other half's identical. Does that make sense? Okay. So, if I scroll up, I think it's going to be a little bit easier. We had that matrix that's called FBGC. And the writing part's ugly. How would I take this information, this system, and obtain this? Did I replace the whole bottom row? Oh, is this supposed to be C or is it supposed to be... Ooh, love it. Love it, love it, love it. So it looks like the bottom row changes. But there's something else that's going on here. Like, clearly the letters are connected, right? Now, here's the really cool part about this. You guys told me it was a determinant of something already. But if we look at this, what do F and G represent? Like, if I... How do I want to word this? The X's, F and G. Careful, not just the X's. I have a C and a G, so that's where your bottom row is coming from, right? Okay, as we look at this, what I see and what you wind up seeing eventually, I'm just going to point it out for us if that's cool with you. Because I don't think it's quite clear here unless you guys want a couple minutes to play around with it. Ooh, one of the variables and the constants at the bottom. I think you're on the right track. Now, even more so, and I'm trying to think of how I want to word this because I want you guys to play around with it. I lied. I'm going to give you like 2 more minutes. How do we go from here to here is a question. I haven't heard the right answer yet. I've heard bits and pieces that sound like they're on track. That's the only question at hand. From this matrix, how do we get this? I'm going to give you guys some time. Talk it out. You might be wrong. You might not see the whole picture. That's fine. I'll show you the whole picture eventually. How do we do it? So check it out. This is a harder question, I think. However, if I asked you how I get this matrix, if I do this instead, and this is just talk it out with me, okay? I don't care if you write this part down. How do I get this matrix? C, B, G, F. So kind of.
Swap the diagonal.
I swap the diagonal. What do you mean?
Like how you do this, but you would, I don't know.
Okay, so kind of. My original matrix was ADBF, right? What did I replace these with? With C and G, my constants that come out of the equation, right? Okay, now, to go a little bit further, now's that spot that you're going to hit. If we just swap it along the diagonal, and this has a specific name, we haven't talked about it, but if we swap it along the diagonal, we get this matrix now. Okay, this is called a transpose, and we get some other fancy stuff. I'm not going to ask you guys about a transpose, but know that that word exists, and it's just what you get when you flip a matrix. Now, going through this, if we want to get these values, we have something super nice that we're going to generalize, and I'm going to give it to us in our generalized form. This is the determinant of here, which language-wise, it's the adjoint of whatever we just did with that transpose, which is really fancy language. We're going to generalize this and see that there is a shortcut to get through this. One last little step is something here, FC minus B. It's a determinant of something over the determinant of A, right? And the big question is, what's the something? And we're going to work it out right here. From this, that question is probably not super clear. I want you to, next little piece, in your notes, we did the derivation. We're going to see the very last piece and generalize it. I want you really big and clear somewhere to write Cramer's rule. Okay, we have a way to solve systems. And with 2x2s, in all reality, Cramer's rule is kind of meh. It's whatever. A 3x3 Cramer's rule saves us so much time, it's insane. All right, so right off the bat, if you give me a system that has the same number of rows and columns, it's a square system. Okay, when we write this more formally, what you are being given is a system of n equations in n variables. And you've heard that language before, 2 equations, 2 variables. Cool, that's a square matrix if you do the coefficients. Now, I wouldn't just write down everything ahead of that, but I'm cool with system of n linear equations in n variables. That's where I would stop. So it could be 2 equations with 2 variables, it could be 3 equations with 3, it could be all of a sudden 4-dimensional math with 4 equations and 4 variables. But we could represent it as a square matrix using coefficient and matrix equations. Okay, beyond that, we have a coefficient matrix that's going to be n by n as well, because that's how many coefficients there are. So go ahead and catch up to this point, all the way up to the determinant's not 0. You give me a system of equations, I make the coefficient matrix, and I determine that determinant is not 0. Okay, with this next piece, we're going to do an example problem together here in just a moment. But with this next piece, it turns out that if you were to take our original matrix and we had, can somebody remind me real quick? A, B, C, D, nope, C, D, F. Okay, if we take this thing, and that was equal to CG, right? Okay. And this is just me talking and thinking. I should have changed to white so you don't write. Okay. If I go with this, if I were to replace this here and get CGBF, if I found its determinant, it's that CF minus BG, what we had a second ago. Okay. This is a weird connection, and I don't know with enough time if you guys would have noticed that that's exactly what's happening or not. Maybe, maybe not. Somewhere in between. Yeah, if this is my original coefficient matrix, and if I'm solving for x theoretically, if I replace the things that are in the first row, my x coefficients, with the answers, I get this, CBGF. Okay, and then we saw a second ago that CF minus BG showed up, right? And I can see it right here is where it shows up on this side. CF minus BG, like we had it a second ago. And we're just seeing where it actually came from. Now, this is the determinant of this matrix, of our coefficient matrix that's been changed. Okay, when we deal with this, here's the rule. And we'll do an example to really make sure that this is super clear. The rule says that, hey, if you want to solve for x, take your coefficient matrix, whatever it is, and all we're going to do is, if this is my A coefficient matrix, here's the regular values that were already there. I've replaced them with the answers, the constants. I've taken the x's out of that matrix, and I've replaced them with the constants that it was equal to. Okay, if I have this new matrix, and I find its determinant, and I divide it by the determinant of A, which we already had up there, it's the same as multiplying by 1 over the determinant, we get the exact value for x. Okay, there's some notation stuff that we could hit really hard. I've included obviously a little bit. Like this thing right here, A12, What do you think that represents? A was my coefficient matrix. What's the 1, 2 about? First row, second column. This is the y coefficient. A 2, 2 is the other y coefficient for this system. I haven't touched those. Okay, it turns out that x is exactly the determinant of that new fancy matrix that we get. The augmented transpose is what it's called, over the determinant of the original coefficient matrix. Now, that looks gross. Does it really seem to you like that's going to solve a lot of issue or save a ton of time? Okay, but here's what I want to do. The problem that you guys did last night and we talked through today, it took like 10 or 15 minutes to do. Like even just to talk through it. Like it was kind of a lengthy problem. I want to look at that one and try to apply this really quick. So, the actual equation that we did last night, and does everybody have this written down? I would do an example underneath, but I want to use the system that we looked at yesterday. It was this one, right? This system, lost it. Will somebody just read me the system from yesterday? That would be super helpful, actually. 1, 3, the actual system. 1x plus 3y equals minus 3y. Thank you. So the one that you guys did last night, theoretically for homework, x minus 3y equals 13. And all right, now we're going to do this and we're going to write it down notationally speaking. I would write it right under your Cramers rule. So let's check it out. First thing, can you find me a coefficient matrix for this? Okay, so I'm going to call this D. All right, it is 1, -3, -4, 1. That's the coefficient matrix. Can you find me the determinant of this matrix D? And that was a question, but I'm going to rephrase it as a statement. Find me the determinant of this coefficient matrix. -11. Okay. Anything crazy yet? Nothing new. Now we're going to make this really crazy matrix, though. That's like the augmented thing with we're going to change some stuff around. We're going to denote this in this situation. I'm going to solve for x first. Cool. dx is the matrix that we get by replacing the x coefficients with the constants. So instead of 1, -3, -4, 1, what am I going to put in that first column? -3 and 1 are going to stay the same, but x changes. -13, because that's this answer. And here, 8. Okay. I've replaced, when solving for x, I replaced the x coefficients. Do me another favor real quick and find me the determinant of this new matrix, dx. What is it? 11? Okay, big moment of truth. If you look at Cramers' rule, and I have some stuff showing here, so I'm going to have to just work this way. X is equal to the determinant of dx divided by the determinant of d. That's what we have written, right? Well, what's dx? The determinant, I'm sorry. 11. What's the determinant of d? And if you checked the notes from yesterday, what do we get for x? Huh. Now, -1 and 4 were our answers, right? Maybe not yours. There was a mistake, not to throw shade, but I think that there was one little mistake. But I think that that's what the answer that checked out was. Okay, help me out here. If I now want to solve y, there's a couple options. With a 2 by 2 realistically, I would probably just take this x and I'd plug it into either of these. That's the faster way to do this. However, can you guys find for me, not can you, find me dy as a matrix? And then I want you to find me the determinant of that dy as well. I know the answer is supposed to be 4 in the end, but we'll see if it shakes out that way. And I'm going to check out the dy matrix that you come up with. Love it. So here's dy. So here's the only thing. If we're solving, if we're doing the y version, we don't change the x's. So there's still 1 and -4. Love it. But then the y's become -13, 8. Yep. Awesome. So with dy, this time we're going to change the y values. So this is still 1 and -4. But then the y coefficients change to what? -13 and 8. So let's see, that becomes 8 minus a negative, so 8 plus 52. Is that right? 4 times 13, is that 52?
Yeah, minus.
Minus 52, thank you, that's 44. -44. So now if I did the same thing and I said, oh, let's just solve for y would be the determinant of dy over the determinant of d. Which in this case winds up being -44 over 11 and is what? -4. Now what did we find as a solution for x and y a minute ago? -4. Did I make a mistake somewhere in here? Where was the -11? Yep, okay. Thank you. Fantastic. Thanks for that catch. Good job. Okay. This method for solving systems, I think and I hope, is a little bit more efficient than actually going through all the inverses and stuff. Now, where we're really going to see value, and we're going to have a homework assignment out of the book over the weekend or off the video if you'd rather, but I want you to do out of sequence here, just a skosh. You need to have a calculator handy. If you need to take the calculator out of your desk, take the calculator out of your desk. Because I did not teach you how to do 3x3s, but we can do them. Now, first thing, do you remember doing 3x3s last year?
Not by any.
Okay, so while you guys are starting to look at like a 3x3 system, not a matrix, like XYZ, 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 where it takes like a whole page of work, did you guys do those? I'll show you what it looks like out of your Algebra 2 book from last year here in a moment. But I have a challenge for you. This is going to be one of your homeworks, so you can put it on a new, or problems from the homework. You can put it on your homework sheet, and you'll have one of them done already. Your homework is, I'm going to call it 9.2.2 because that's what this is called it, or that's what it's been called throughout the CPM stuff that we were using. It's really chapter 8, but that's okay. Like, we'll deal with it. Your homework this weekend is going to be 8 through 16 even. Now, for this is going to feel wonky. I want us, and let me verify there's going to be an answer out of it. I want us and you, all of it, whatever, to work, and I think it's number 16, but let me verify it. Let's do number 16 first. So I'm just going to copy just number 16. And this is in your regular textbook. There's a picture of it right here on the video if you want to eventually use this instead of taking your textbook. Your textbook presents the same stuff and more, but in a bit more detail. For the time being, I want us to just do number 16. So I will come all the way up here, and I'll just erase a bunch of stuff. And I want to look at number 16 kind of together. With you guys are using the methods, the Cramers rule, and some calculator stuff to solve it. So here this is. We have 3 equations, 3 variables. Could you write me the coefficient matrix? Okay, we need it. There's 2 things that we need. The coefficient matrix D, we can write no problem. What's the first row? 5, -4, 1, -1, 2, -2, and 3, 1, 1. Everybody good with that? Okay. For this, there is a way to get a determinant of this. We didn't do it by hand. Can your calculator find this determinant? So before you do anything else, especially since we're using the calculators, I would suggest Let's find the determinant of D real quick. It is on your calculator. Do you want me to show determinants on a calculator one more time? Okay, if not, I'm going to pause it just so you guys can get the determinant. As you're calculating it, I'm going to put a little bit more stuff up here. I hear 33. I don't know. I haven't done it. 26. So we got 2 answers so far. 33 and 26 are the 2 that I've heard.
Mr. Holloway.
Interesting.
Is this showing up? Oh wait. Why don't you show up as another picture?
You said A times. You did A times the determinant of A.
Oh, I didn't even realize I put that.
Okay, so I'm just going to check your matrix real quick. Okay?
Yeah.
All right, so on this matrix. Edit. 5. You forgot your negative here, just so you know. 5, -4. That's where it's at. Okay. I'm going to do it real quickly as well. Anybody type it in again to see? Did you get the same thing? Okay, so I'm going to edit mine real quick. It's a 3 by 3 deal. And we go 5, -4, 1, -1, 2, -2, 3, 1, 1. Okay, got it. It's saved. When I ask my calculator for the determinant of it, I'm going to go to do some math, find me the determinant. I'll put matrix A in there, and let's just see what we get. I like 33. Okay. As soon as we have this, and I'm going to keep you guys for like 10 seconds, I want you to help me make this one randomly. I want DZ now. Like, this is going to be used in every calculation. To get DZ, what changes? The Z's, right? The last one. So this matrix is still 5, -4, and -1 and 2, and 3 and 1. But what am I going to replace this last one with? -14, 10, and 1. Could your calculator find the determinant of that? And Cramer's rule will tell you right off the bat what the determinant is, and then what's the value, and you can get it. Okay, over the weekend, take your calculators with you. You have to have them, or you have to be able to Google matrix calculator because they do have them online. I want you to apply matrix or Cramer's rule to these. You only have like 4 more problems to do other than this. Cool. All right, appreciate it.
Thanks, all.
Cramer, no worries. Cramer's rule for 2 by 2s, meh. Cramer's rule for 3 by 3s, huge efficiency boost. All right, later Raiders, I will collect the homework on Monday.